Okay, bom dia, good morning. So let's get back to our numerical Pdes review. Which I'll basically finish today. So let's look at the convergence theorem. For explicit Euler. Okay? So it's simple, not always it's simple to prove convergence proof for numerical methods, but we're going to see today theorems that simplify our lives. Here we're going to see in all details. I mean, all details are in the notes, but the proof is in all details. Okay, I'm going to do some parts of it. So the theorem is like this. So we have, let me write in a, so the hypothesis, our solution, is between this interval. Second derivative bounded by m for all, right, for all x. This interval, so x, let's think of it as time. Let me do, well, our differential equation. Is this with this. So this is the hypothesis. Okay, I'm writing it in a sketchy, fast way. I'm going to call E0 the initial error. H will be the same as little x. L is Y's Lipschitz constant. Okay, and here's the result is that then we can do this estimate. Okay, so basically this is just to make sure we have all the hypotheses, the usual hypothesis for ODs and so on. So if we're using the explicit Euler method, we can write this inequality. As I mentioned last time, we might not always be able to satisfy the initial condition because of finite precision. So that's why we put this little error here. And this is where, let me highlight this. This indicates that then the method is first order. Okay, so it's not difficult, right? If we've never seen this, we have to, we'll take a little time getting things together. But let me do the sketch of the proof, where the details are in the notes. Okay. So as I mentioned, in principle, the notes are in Portuguese, but those who are watching and do not speak Portuguese, I mean, you can follow exactly the points. I mean, the points I'm skipping, there's even no words. It's just calculation. Okay, so this is how we do it. So let's get the exact solution and Taylor expanded, right? The exact solution is this capital Y. Or better than saying that Taylor expanded, and as I was talking to some of you, let's do a polynomial, Taylor polynomial approximation, which here you already see without me putting any details. This is the error. Now here we have our numerical solution. Okay, and any doubts? Any doubts? And here is our numerical solution, right? Here we see Euler's method, and this is just to indicate as n goes up and so on. Just notation that, you know, it might not hit, right? As the spacing keeps on changing as n goes to infinity, it might not hit the capital T time that we're interested in. No big deal. Okay, so now if we subtract these guys, right, I can write this. So let me skip some easy steps and go directly to this. Let me copy to get it right. And I'll mention in words what was done. And it's easy for you to follow. I am absolutely sure. It's simple, okay? Well, the same values for n. So what was done here, right, very simple, right? Subtract this from this, definition of the error, right? Subtract this from this. Whoops, I forgot something here, didn't I? No, yeah, this is wrong. Okay, yeah. I was thinking, I forgot a power, but this is wrong, right? No, I got it. So subtract this from this, subtract this from this, is this guy, subtract this from this, use Lipschitz, right? And quote the second derivative. That's the m. Okay, easy, right? Now, and that's why, sorry, that's why I stopped here. I thought I had a mistake. Now we can use recursion, right? I can use this formula for this guy and use it again, and use it again, and use it again. I'm going to get powers of this, and I'm going to land at the end at E0, right? And that's why I was looking for something which I made a mistake by putting this. And this is what we get. So using recursion, then let me copy also so I don't get mis-exponents. Okay? So it's, you do a few times, you're going to see that you get this form, right, using recursion. And then we can actually write one more step. This oops. Okay, you can guess what I did. Just basically this goes from, say, 1 to n, right? You sum this guy, you get this guy. And now, okay, I'm going to also skip one line here from the notes, but I'll tell you what we're going to do is that this guy here, this guy here, okay, we're going to be able to estimate it like this. I didn't have to put this. Let me put the final result. But then also now let me put it this way, use that this, and you will probably guess, let me put the result. I'm skipping very few things. I think I should put this intermediate step just so we can communicate properly here. Capital N. No. See if I don't say anything, you guess more or less what was done. Okay, then let me say I put the N, since I'm talking and writing, sometimes I got all mixed up. Yeah, I think I got it right. So this guy here, and then we're going to use this result back here. So this guy here, this is simple, okay? Look, this is this guy here, no big deal. Now, what the step in between here is that this is smaller than this guy, little n, with capital N, right? Because capital N is the largest n that I can have. Look, that depends on the h and the spacing as I'm taking the limit. And then with the capital N, I can estimate these guys. I get the h is, of course, smaller than this. And this guy in the limit is the definition of that. Okay? So double check that. This is the definition. So I plug this, I will plug this, use this up here to then basically get the final result. Right? I'm going skipping a few steps. You do as an exercise on your own, or then double check with the notes. Let me just put this like this so to highlight what I had mentioned last time. Okay, so what am I highlighting here is that this h cuts with that h, which was something that reminds us of that sort of asymptotic way that we can quickly see that if I have the local truncation error h squared, and it accumulates n times, n scales like 1 over h, and therefore we lose a h as the error accumulates. This is basically showing in the right concrete, rigorous way. The other one is just an asymptotic thinking. And so we arrive to this result. Okay, so therefore, Euler's method is first order. Okay, so this is simple, right? But because the method is very simple, and soon today I'm going to mention, right, very soon now, some more powerful tools in a very powerful theorem, which is really a beauty, and to prove it, it's not trivial. It's in some of the books. Right, Isaacson Keller's one that has some parts, but I'm going to tell you the theorem because it's very nice. Two theorems which are very, very useful. So let me first give the notion of, so I can mention about the theorem. I think I already mentioned this last time, like consistency, which has to do with local truncation error. So let me call this my discrete, in our case, finite difference operator. And consistency means, in the way we've been defining things, this. Look, I'm being very sort of telegraphic, right? Some of you maybe don't even know, too young to know what a telegram is, but of course, you know, telegram is it could be an applet, but telegram was a long, long time ago when there was no internet or anything. We had to send messages in a very short way because every letter was expensive, right? You don't want to add letters. So this, what am I saying here? I'm saying that 1 over h, the discrete operator will turn to this. So for example, if you think of local truncation errors, right? I'm already talking with few words to experts. If I put here in the dot capital Y is the solution of the ODE, right? This guy here will have a residual. It's not equal to 0, right? And remember that last time, I think it was around these boards here, I said, oh, if I divide by h, right, it looks like for Euler's method, it looks like the definition of calculus, of derivative, okay, remember? So therefore, and in the books, I think usually we don't get confused, but the definition of local truncation error sometimes vary from one book to the other, because in some books, it is divided already by h, so it looks like the operator. In other books, it's just like the residual of like the numerical method, right? And the method is consistent, okay? So this is one way of talking about consistency, or the method being consistent, which means the local truncation will go to 0 and so on. So, or this, which is another good way of thinking of it. Because last time I mentioned to you that consistency and stability, which is a theorem I'm going to mention soon, first theorem by Dahlquist, famous guy from numerical analysis school of Sweden, prove is that convergence is equivalent to consistency plus stability, zero stability, which is like the numerical scheme being well posed in a parallel with ODEs. Okay, so consistency has to do with operators being close, and stability has to do with solutions being close to some extent. You have some control. And those two ingredients, there's this powerful theorem by Dahlquist that said, hey, that's the same as having convergence. We prove convergence here in an easy case, but it's not that easy always. Okay? So this is one way of seeing consistency. The other one is also seen sometimes like this. Okay? Local truncation error divided by h goes to 0. So this means that somehow means some sort of a or proximity in sort of an, right? In an asymptotic sense, right? This guy will converge to that guy. Whoops, I put minus here. Sorry, I'm talking and I forget. So when I mention it, it's tending to that. It's not minus. Sorry. If you see something like this, because I'm talking, writing, look at my notes, complain, okay? Even if it looks simple. So this means that this object here will tend to the continuous operator. That's consistency. Okay? So let's see how I do this. Yeah, I don't want to erase. I'm being not very calm. Let me go to the other board, because then I have to write. So we're going to, let me put just one here thing. So consistency. And we will soon see the definition of what's called zero stability, which, let me actually introduce one, which reminds us of the notion of well-posedness for ODs. That is continuous dependence on data. Okay? So let me use here, for example, to refresh our memories. So right? As the definition given in Udi Asher's book, which is one of the books I have in the library for numerical methods. So I'm taking that from his book. So we have the following. Let me also put in a sketch away the well-posed for ODs, so we can contrast this with the one for the discrete operator. This would be then for the continuous operator. So this, let me write in a way that I can move fast, right? Sort of a sketch away. Continuous for all yx in this set D. Like this, in case it could be for systems too. So we have a time interval 0t. Okay, yeah, he uses y. It can be a system. And y and put y in and. Y is Lipschitz, okay, with constant L. So then he puts three consequences of this. So for all y0 equal to alpha, alpha and Rm. It's putting m, so because n usually will come later for it. Right? There exists a unique solution y in the interval of interest, 0t. And for the initial value problem, and the solution is differentiable solution, of course, with y, of course, differentiable, satisfies in the usual way the ODE. Y of x depends continuously on data. Or on initial data. He first mentioned this initial data. Okay, and has here an estimate. I'll skip the estimate, just put the second one, which is the most important, I think, for us to connect this with zero stability. And let me write this a little better, because I'm translating and writing at the same time. Let y tilde satisfy the perturbed ODE dy dx equal f yx plus r yx r bounded by m, right, taking some norm. Then might want to get an estimate like this. Okay? So usual conditions for an ODE, right, system. And this is the important thing, that we will connect ODEs with differential equations with difference equations. Okay, so this estimate here looks pretty much like even the proof, the structure of what we got for the Euler's method. So what we're saying in this version, right, is that if things, the ODE depends continuously on parameters and so on, and also if you perturb it, right, and this is bounded, and if this is actually epsilon, if this is smaller than epsilon, you have an epsilon here, right? So you have the difference in initial conditions, and here the control or the perturbation, and somehow here the proximity of the solutions of the two systems, the unperturbed and the perturbed one. Zero stability, and I think this is why this version is in Uriashi's book. It's a book on numerical methods, right? And I know that, for example, some of you that took ODs, there's in Marcelo's book with Jose Espinar also versions of this, and right, that proved in all detail of continuous dependence, right, of ODs and so on. So we're not going to prove this, of course. I just want to contrast, and I think that's, Uriashi doesn't prove it also, but this is just to contrast. As I mentioned, if you look at Lambert's book, all these books specialized in numerical ODs, there's a lot of definition of stability, each one for its own purpose, right? Absolute stability is very useful, as we saw. It's very simple, but very useful. We can see, for example, Spear's artificial damping, as we saw. And this one is very good because you're going to see a parallel of this one with zero stability, very likely inspired by this, and which was the means for people to prove some very super powerful, in my opinion, theorem, as I'll state next. So first I have now, using this, just to create the parallel, give you the notion of zero stability. I think it's good because if you see zero stability, where does this come from? Well, I think it comes from here. And then you see the theorem that uses zero stability, which is the very powerful theorem that says that zero stability and consistency is the same thing as convergence. Okay, so that's the idea of what I'll be doing next. So I have to come to this board here, far away, but it's okay. So where is yours? Here it is. No, here. So now, case of difference equations in contrast to differential equations, right? So we have two difference equations. LH is our discrete operator, yn equal to 0, y0 equal alpha. Then we have LH, Zn equals an Rn, sorry, it's capital Rn, doesn't really matter, but just, and Z0 is alpha tilde. So this basically plays the role of like our perturbed equation over there, okay? And look at this. This can plays like the role, the analog of our perturbed equation. And it also if you think of Zn, I'm using the notation of the book, right? And I think I'm following Lambert and Asher. This could be, if this is the exact solution of the ODE, it does not solve the difference equation, right? So just notice, just notation in words. If this is the exact solution of the ODE, it does not solve the difference equation. So this perturbation, if I just made it minus this equals 0, this perturbation is related to the local truncation error, right? This Rn is playing the role of the local truncation error. So cool. So okay. So then we say, okay, now the definition. So we say, so the method is zero stable if there exists constants A and H naught, so that me see if I have this right. Okay, so if you, as you can see, this has a flavor. Okay, this can be thought as a definition or something for you to prove, right? First, let's see it as a definition. As a definition, it says the method, this is basically the method, right? Our discrete operator is zero stable if it satisfies this, that I can find constants A and H naught. H naught basically means that there's sort of an upper grid size from which, for finer time steps, I can sort of control things. Maybe I cannot control it for all H's. I can only control it when H is getting small enough, when my resolution is good enough. Okay, this is what this means, right? So you say, oh, I cannot prove this for any H. No, but if H is small enough, I can prove it. Okay, fine. Prove what? This inequality. So this is first, I read it as a definition. Zero stable is if the solution of the homogeneous discrete difference equation minus the one of the perturbed one is bounded by this, then I have to find this constant, that's the other constant there, such that this is the error in the initial condition, this is sort of the error or whatever the difference is, because there's the residual and so on. I can control it for all time, and maybe the max of this. If I can control these guys, then this is said to be zero stable, right? With a more, so this is the definition, but this definition, you know, sometimes written maybe as a theorem. It will be a theorem if you say, oh, okay, get a method, LH, and now prove that it satisfies this. Then you just prove that the method is zero stable. It could be a big headache, right? It could be very difficult depending on the method, right? And we're going to see a super nice also theorem that makes life simple, okay? So I'm going to mention two theorems, and that altogether makes things very beautiful and simple. So this could be very hard to prove, right? But so let's see it as a definition, right? And as a definition, if we prove this, it's called zero stable. Okay, why is zero stable important? Because look at this definition compared to that one over there. It's a little bit of a discrete version that this has continuous dependence on initial conditions and perturbations. Okay? And now, as I mentioned before, I'll repeat it, this perturbation here, right, can be thought of, can be playing the role of the local Chartesian error if I think of Z as capital Y. So this would be like Yn minus, like this, right? If we think the perturbation. So cool. This zero stability is a discrete version of being continuous dependence and so on. Okay, and as I mentioned, it could be hard to prove, right? But it would be nice to have this because then there's this super theorem here, sometimes called, there are many theorems that are called equivalence theorem. Let me just write this one theorem, and one first version was by Dahlquist, 1956. Okay, did I write Dahlquist correctly? I think so, yeah. And he did the first proof. The first proof is for linear multi-step methods, where linear, I'll tell you in 1 second, or else I'll stop here. Linear does not mean that the ODE is linear. Okay? Or else I stop here. I'll tell you in just a second what the linear multi-step is. Okay? So just think, okay, Dahlquist, first proof of this, and the theorem is just, you can write the theorem like this. Okay, sometimes called the equivalence theorem, equivalence because of this. Okay, sometimes called, let me put it just here as a reminder, sometimes called in OD, but there's then another famous one, which is the equivalence theorem in PDs, sometimes called the Lax equivalence theorem, okay, with Lax, Rick Meyer's name appearing. So what does this mean? This means if and only if, right? The equivalence, right? So if you have consistency, zero stability, you have convergence. And, right, I mean, you can't add words and whatever, but the meaning is that if you have somehow an asymptotic proximity of your operators, difference with differential, and you have, right, zero stability, which means proximity of solutions in this way we're seeing here, right, continuous dependence, then bingo, you have convergence without having to the whole trouble of estimating everything and so on. But still, this is hard, right? This is still can be very hard, right? It's like proving well-posedness of differential equations, in particular PDEs, is an area of research here at IMPA. People of analysis are proving this all the time. Well-posedness and continuous dependence on this, on that, for complicated PDEs, right? And for numerical methods, sometimes with discrete operators, discrete things get, sometimes even, go back here. In convergence, if we're able to estimate regarding convergence, I was doing xn, right? So if this can be shown, right, then it implies, very simple, just to be complete, okay? You knew this, but just since it means the method is order P. Okay, so now, okay, good. So now let me make some observations. So here's an example of a linear multi-step method. And it's important for me to show you because then it would give you the definition of what is a linear method without the equation being linear. And that's going to be important for the root condition, which is a very nice condition related to zero stability that makes our life easy with zero stability. Okay, so linear multi-step method. So here's an example of a linear multi-step method as it appears all over the book, for example, of Lambert and so on, and written here in sort of a generic way. Okay, so this is a linear multi-step method. Okay, we have this. Okay, so the OD is not necessarily linear. It's a general OD, for example, for a scalar problem. But the method is called a linear multi-step method. It's definitely multi-step, right? Has k steps. And it's linear because of this. It's a linear combination of the vector field. Because that's why it's called linear multi-step method. So it's a linear combination of, for example, these guys. So, for example, Rangakara 4 is not a linear. It's not a multi-step method to start with, but it's not a linear method. Because as you see, the vector field acts on the vector field, so it's kind of, it has this sort of recursive action of the vector field on the vector field. On the other hand, the Adams-Moulton and the Adams-Bashforth is linear. You gotta save information from the past, but there's no F acting on the F, right? If you go back to Rangakara, you see that, for example, K2, remember Rangakara was K1 plus 2K2 plus 2K3 plus K4. K2 is the vector field acting on K1, which depends on the vector field. So there's a vector field acting on the vector field, okay? So if you have a guy like this, okay, and there's some hypotheses, normalization hypothesis and so on, so the highest guy is 1, alpha 0 plus beta 0 is different from 0, so that, and then you can associate to these guys, right? You can associate with these guys the following. So, and we have the following characteristic polynomials. Rho of zeta, and sigma of zeta, this is called the first polynomial. I'm put like this here. First poly. This is called the second polynomial. Okay, and you can see where these guys are coming from, right? This and this part. Okay, and here's the root condition. And then we're going to use the root condition. What is the root condition? The root condition says this. So you find this in all these books, Lambert, Isaacson, Kessler. Let ZJs be the roots of the first polynomial. Let me write it here again. Rho of zeta. Then zeta j less than 1. So read this, okay, as I'm writing and translating at the same time, right? Which, and then I trip on the thing. So help me here. So read this, that you satisfy, I won't rewrite this, right, as I'm translating here in real time. So we will satisfy the root condition if what I'm writing is okay, okay? So the root condition means that let zeta be the roots of that first polynomial. So we are satisfying the root condition if these guys are less than 1, okay? So then, so the root condition is satisfied. Well, let's see. I'm seeing your expression, your face is not very happy, so that will be the root. So root condition. Let me write this back. Okay, I'll not be too lazy. Root condition is satisfied if less or equal than 1 and if for some j, right? Then if for some j, zeta of j is equal to 1, then zeta j is a simple root in opposition to a double root. So sorry, because I was translating, so let me read this again with you, okay? The root condition is ZJs are all the roots of this polynomial. Okay, that can be a degree depending on how many steps I'm using my multi-step method. Okay, cool. Now, the root condition is satisfied if all the roots are less or equal to 1, and we might have a double root, right? And if there's a double, but if the double root or the root, which is on the circle, right, has to be simple, cannot be a double root, right? Can anybody guess? Let me take a drink of water. And can you think why? I mean, I'm throwing things at you, but just take a while to guess. Why this restriction that if there's a root on the unit circle, it has to be simple. It cannot be a double root. You can have a double root inside. I'm going to show you soon something that sort of triggers at least my intuition with something very simple, undergraduate. But as I told you, many things that you shouldn't feel bad. I say, oh, this is undergraduate. And you think for more than 3 seconds, 5 seconds, because this is new. So that's good. The fact that there's an intuition behind that's simple is good news, right? But let's first exercise. Why does the root on the unit disk have to be simple? You can have a double. First thing, look, I'm going to already tell you something in advance, which I already mentioned, and to make you look happier than you're looking right now, which is this root condition. There's a proof, and I'll write it down, that the root condition, as you think, I'll write it down, the proof that's that root condition is equivalent to zero stability. So if you check this for this class of methods, right? So there's a theorem. You find it in the books. Lambert, page 35, has this, that root condition super cool, right? I mean, not easy to prove, but super cool, because this is much more simple to verify than this, right? And this also is super cool, but for methods of this type, right, which are linear multi-step methods, combinations like this of the linear combinations of the vector field, blah, 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 okay? But super cool, super useful for a class of methods that you just verify the roots, right? Sometimes if this polynomial is of high degree, right? I mean, you have to check it numerically. Right? If they're smaller than 1, the simple, but fine, right? So basically, root condition plus checking consistency, which is also simple, right? You have the convergence of some methods. Super, super easy. So let me erase the board, and I'll tell you why this root on the unit disk has to be simple. Cannot be a double root, for example. So just get in, because it gives us intuition. Okay, that's not what I want. Okay, it's not, this does not tell us exactly the proof of the root condition, right? It's more sophisticated, but gives us the intuition. In particular, answering this question I've just asked you. So look, if I have this equation here, this homogeneous equation here, right? How do I solve it? Well, I solve it by taking basically a guess of this type, right? I mean, in the PDEs course that I taught, some of you use the words ansatz for sort of an educated guess for the solution. Well, is the solution like this? Well, it's not like this, but if it was just like, right? Particularly if it's like this, we know that it's got to be an exponential because you differentiate it twice, it's the same guy and so on. Well, you plug this in here, you get what? The characteristic equation or characteristic polynomial, if you like, right? So this implies the characteristic equation or polynomial, which will be a lambda squared plus b lambda plus c equal to 0, and then you find your solutions. Okay? If you have a double root, then our homogeneous solution will be like this. Right? And if we think of x in time, when we did the PDEs course, and some of you were there, this had to do sometimes with resonance and, remember, secular solutions, so just as a comment. Now, if we have difference equations, okay, so here we have a differential equations. If we have a difference equations, right, there's some books which are very good examining all sorts of solutions of this. One book is actually Bender and Orszag. I mean, but you don't even need to go there, but anyway, Bender and Orszag is a very good book in terms of methods for asymptotic methods for ODEs and differential and difference equations. Okay, it has asymptotics and so on. Now here, our guess is different. It's r to the n instead of e. This gives us the characteristic polynomial or the characteristic equation. Okay, I'm not even gonna write it. And in the case of double roots, we have that yn will be equal to C1 or not the yn, but one of the components of the solution will be like this. Well, in this case would be y, yeah, because it's for one of the roots, right? Because there's other roots. So for this component will imply, so look what, right? So did I go too fast? Right? So this double root here gave us this, where is it? Where is it? Yeah, here. This double root in the continuous time, if x is time, gave us a linear growth in time. This happens, for example, when we have resonance. But here, we don't even have a forcing, so it's not right. It's not the right. The word resonance is not the right word. Sorry, but it gives us this growth. And now, for this case, we also have a growth in time, discrete time. Right? So if the root of that polynomial is on the unit circle, you're going to get some instability. Okay? Whereas if it's inside, right, it's going to be raised by, it won't generate that. So that's a bit the intuition for the root condition. Okay? And this basically, good. I have half an hour approximately to now start talking about PDs, which was what I kind of was planning. So this ends our review of ODEs. Quick review, schematic overview of ODEs with setting the language, setting communication between us, and talking and so on. So some very nice things, and as I mentioned too, there's just entire books just on numerical ODEs. Dahlquist is a very good one, Gear, and so on. Okay? So now I want to move to very simple. We're going to start with very simple. Actually, the PDs in the whole course, not all the time, are going to be pretty simple. And so let's now migrate to to numerical PDEs. And at one point I will mention the equivalence, I will just mention it, also will not prove it, the equivalence theorem, Rickmeyer-Lax or Lax, which is the equivalence theorem for linear evolution equation in this spirit, that consistency plus stability, it's not called zero stability, but consistency plus stability is equivalent to convergence, which are very, very nice theorems. Okay, so back to simple stuff and back to notes from a short course at IMPA. So now let's get to numerical PDEs, and I'm going to start with an advection diffusion equation, which basically means wave plus diffusion or a heat term. And let me tell what the simple model that I used in this course, which was a colloquium course at IMPA a long time ago, was showing students modeling. And the idea was this. Was this? There's a factory that generates pollution. You have a house at a distance, and a very simple model to see how much pollution would reach your house if the worst case condition blows with the maximum wind in the direction of your house, and if this wave has a concentration of the pollutant xt, right? This is the concentration of the pollutant at position. So at initial time, for example, right, mathematically at initial time, I would have this, right? So it's a unidimensional model, right? It's a bit of an exaggeration, but the cloud has constant concentration all over it. Boom, discontinuous. That's not how it works, right? I mean, but okay, a simplified model. My house is there, and then the problem would be like this. Whoops. Very simple problem, right? To teach students a little bit of modeling, and in reality, of course, the models are more sophisticated than this, but to teach them how to do the modeling and to see the shortcomings of the numerical approximation, just like we saw for ODs. You can also see spurious, in a very simple way, you can see spurious behavior for solving this problem numerically. Remember that in OD, the spurious behavior was the artificial numerical damping of the oscillator. Okay, here we're going to see artificial diffusion. And then you might get confused because you have diffusion in the problem. So it's very interesting that when you have a problem with many physical ingredients, to test parts separately before you put them together and understand what's going on. So that's the idea of this part of the lecture, and we'll continue on this next excuse me, next class, okay? So CX, C. Okay, and then at some point I will talk to you also that this problem, this PD here, the wave equation, is a linear one, does not generate discontinuities, but we could, for example, in this case, have discontinuities in the initial data. And what will the numerical method do to the discontinuity in the initial data, which from the PDE's point of view is a non-classical PDE. In my PDE course last semester, we talked about this, okay? But this is for the future. Let's just think that this is okay. And look, if I have kappa equal to 0, so this is just transport, and we should see the little square or rectangle moving to the right with speed u. That's the wind blowing, right? Another example is no wind. This means we have the heat equation, okay? And then we have just pure dispersion of the pollutant, which is similar to putting a little drop of ink in a bucket of water, right? You put a little drop of ink in a bucket of water, you see it's a red ink, it starts fading away, fading away, fading, and we can't see it anymore, right? Due to molecular diffusion, right? And the word, as I mentioned also in the course of P, the word dispersion is a little bit unfortunate because, okay, it means two things sometimes. Dispersion in this physical sense of pollutants and whatever, and when we do a Fourier analysis of numerical methods, even though there's no dispersion, we call it dispersion analysis, which is a Fourier analysis. I'll come to that in this course. We'll see that. Okay? All right. So we have to learn. We should start learning this problem, and then putting the two together. Because as you will see, and this is the main reason I do this, if you start solving with the whole problem, you're going to get confused with the diffusion. Okay? Let's see if I have time at least get close to that today. I'm not so sure. Okay, so if I gave this problem to you, right, and you could do it, right, using, I say, look, use finite difference, which is what we did, which is use Taylor series to approximate your operators, right? So that's very simple. So for example, first case, I mean, in time. Okay, look what I have no experience in this problem. Somebody gave it to me. I'm going to try to do it as simple as I can to understand. Don't do it complicated. So we start like this. So I'm going to write this in full. Oops, not the J here. So that we can set the notation. Okay, and this is going to be, now let me sort of already simplify the notation. This is good. Okay, so can you see what I did? I skipped, right? I'm skipping just one simple step. This is a Taylor series expansion. Okay? I did a Taylor series expansion with this guy from here. I get this guy plus higher order terms, which I threw away, right? And then I divided by delta t. And this is just, or in other words, that's why I'm doing it so fast. This is basically explicit Euler in time. And look, I said, oh, explicit Euler sometimes is good. Yeah, here it is. This is explicit Euler in time, using the Fourier, the Taylor polynomial, the Taylor series expansion, only in time, because it's a partial derivative now. It's a PDE. So I'm doing the partial derivative. J is my spatial, and N is my time thing. Look, if I'm in space-time, this is node J, N. This is delta X. This is delta T. Right? Now I'm going to live on this 2D grid in space and time. No big deal. And then I do now, let's try to focus on this case first, okay? So on this part of the equation, the transport part. Okay, so I need to find an approximation for the derivative in space. Also Taylor series. Okay? And let me think you a little bit, see if you want to complain about something, feel free to complain. Let me write the numerical method. The numerical method will be like this. Okay, very simple to run it on MATLAB, the code, the software you want, on MATLAB or Octave, I mean, all these similar ones. So here is for a method, numerical method, for the unidirectional wave equation. Unidirectional because it propagates only this way. Later we'll see that second order wave equation, which is the classical one, has waves in both directions, right? This is the unidirectional wave equation if you put this equal to 0. Okay, so look at this. Let's discuss now. It's our first PDEs in the course, right? Very simple PDEs. You don't even have to know PDEs, right? We know that actually the solution is like this, right? You can do it by inspection, or you can do it using the method of characteristics. For those who haven't seen the method of characteristics, I mean, I did in the PDEs course last semester, but very simple. I can do it in no time here to refresh your memory. Right, so it's basically the initial condition in a moving frame with speed u, which is exactly like this. This is the numerical the exact solution. And are you okay with this numerical method I did? Look, I did Euler in time, and what did I do in space? I thought some of you would complain, or maybe you might defend me. You might come against me or defend me, as you wish. Is this method okay? Is there a difference? Is there a difference in the sense, right? Is it something different between my time discretization and my spatial discretization, or are they exactly the same?
One is forward,
Yes, perfect. One is forward, very good. One is forward and the other one is backward. So that's very difference. So this is a forward Euler, and this is like a backward. It's not, I'm not call it Euler because it's not even time. This is a forward differencing, and this is a backward differencing, right? So this is. Right, look at this. This I went from n to n plus 1 forward. Okay? And this one, I went from, I used this guy. Right? It's kind of still forward in some sense. Now let me see. No, because the PDE is evaluated here. Okay? Yeah, so here. See, this is the PDE. Just think of this evaluated at Jn. Okay, I'm going to use this. I don't know if I have time today. Maybe the next. Yeah, maybe I'll get it started next. I'll use this. But this is like the PDE evaluated here. Okay, and then I do the thing. So it's like going backward, right? Because the second derivatives have to be evaluated here, right? And there's a reason for that, right? Why did I do one forward and the other one backward? Does anybody, I mean, probably some of you might have seen this, whatever. There's a reason. Why did I do it this way? While you're thinking 1 second, let me just say one thing that is very common in numerical PDEs is that sometimes we mention about I'm just curious to know how many of you have heard this, the molecule of the method. Have you heard what's the molecule? We're not doing chemistry here, but there's the name, the molecule of the method. Nobody knows what the molecule of the method is. Good, it's this. This is very nice. It's very good. Once you get the intuition, say, oh, what's the molecule of your method? It's this. You already know. Oh, okay, you're doing forward in time, backward in space, only using one neighbor. If the molecule has more atoms, you know it's multi-step or whatever. So this is the molecule of the method. Okay? No big deal. There's no chemistry. It's just because it looks like a molecule. But this is very good. Because this molecule, if we think this as like a checkerboard, a lattice, right? It is a lattice, right? But like a checkerboard. With a molecule, you boom, boom. It's like putting pieces of a puzzle. As you advance, you see in an intuitive way how information evolves on this discrete domain. It evolves according to the molecule. Because later on here, I'll put this, and put this. Then for this guy, put here. You see what I'm saying? Right? So the molecule is very good because it shows us how information is propagating on our lattice. Okay? Now, I've chosen, not me, this is a classical method. I've chosen, and this example is good because it expresses the name of the method. That's why I do it also. I've chosen, or it was chosen, this molecule, and therefore forward in time, backward in space, for a good reason, intuitive reason. Anybody has seen this and can help me? Okay, time is up because either you know or you don't know, but that's good. The course is for that. Let me actually give you, before I answer to you, let me give you the classical name of this, even when the problem does not have pollutants and does not have a wind. It's basically the name, I don't know why, I don't know why it came with this, but this method is called the Upwind Method, right? Even if you're doing with fluids or whatever. It's called the Upwind Method. But the real good reason for this being called the Upwind Method, and if you don't remember this method of characteristics, right, I'll maybe refresh it to you at one point, because basically the PDEs course that I teach and this course and fluids are 3 courses that I teach it in whatever order the students or I am available. And there's no real prerequisite, because if you learn one before the other, it's helpful. But I won't tell you which one you should learn before the other, because if you learn fluids before PDEs, then you'll be hungry to learn more PDEs. If you learn numerical methods before, you'll be hungry to learn them, and there it goes, okay? So therefore, sometimes I give a little bit of a refresh. So you see the characteristics here for this problem are in this direction, right? I'll tell you what the characteristics, I can tell you in just a second now, actually. And therefore, this is how information flows. See, the characteristics for this problem is so simple. Let me do it here. That if I write like this, whoops. See, this is the total derivative of c with respect to time, which is, you see, the solution at the end depends on space and time, right? So if my inspection say, oh, the total derivative is equal to 0, that means that the derivative, partial derivative with t, partial derivative with x, and x with t is equal to 0 if dx dt is equal to u. So this is a little quick inspection. So this is the characteristic. dx dt is equal to u. So this is the speed at which, if I'm in a moving frame, I do not see the solution changing. Well, if I am on an airplane with the same speed of the cloud, I do not see the solution changing. Right? And this is already going to give us a hint for this. Look. This is the official exact speed of the cloud, and this is the numerical speed, right? So this number, which will be called the courant number, is a ratio between the exact speed, which comes from a method of characteristics, and the numerical speed, dx over dt. That's a numerical speed. And we're going to see stability impacts due to this number. And this guy affects numerical diffusion. This method, Upwind, is good. It has a stability condition. It's not unconditional stable. It's conditionally stable. And it has to do with the courant number, which is this guy, which is a relation between these two speeds. It has to be smaller than 1, which means the numerical speed has to be greater or equal to the exact speed. If it's smaller, poof, you're dead. So the choice of the molecule is already showing that we're in the correct direction. It's not that difficult to do. If you did a numerical method that was like this, for this problem, okay, it's an exercise. I might give it to you. If you do this for this problem, it's going to be unconditionally unstable. There's no delta x, delta t that does the job. You're in trouble. Cool, right? I mean, the mathematics, of course, the molecule is intuitive because things are blowing this way. Well, and even if there's no wind, this is a hyperbolic system. For those who've seen some PD, it's a hyperbolic system with characteristics going that way. So the numerical method should be putting information in the right direction. And the molecule is very good for that. Okay? Let me maybe just finish today, and I'll come back to this Thursday with then, right, the heat case. Let me maybe do it here so we're nearby. So for the diffusive component, we do that okay, so this is how you approximate the second derivative. This is called the central difference. Okay? If you do the Taylor series steps, you'll see you by taking this sort of one guy from each side, blah, 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 you kill the first order derivative because you actually want the second order derivative. And you get a higher order term. Anyway, you'll see when you divide by the x squared. And then here is the advection diffusion scheme. I put it like this. Advection diffusion scheme. So here's the molecule of the method. Okay, this guy came in because of the diffusion term, but the transport is done like this. Okay, and also note that the method is explicit. Right? What does it mean? Look, the only term in the future is here. And actually, this is seen also by the molecule. We'll see next class a term, a method which is better than this one, which is implicit. So it might have, right, more terms on the upper level, right? This is the n plus 1 level, and this is the n level. So this method is explicit and very, very simple to program, right? Put it on MATLAB, whatever code you want to do, very simple to program. Okay, and once you program this method, okay, so even though we saw them separately there, you might want, okay, I'm going to program this, but it is instructive that when you program this, you first put kappa 0, so you switch off diffusion, and you study the stability due to transport, due to the hyperbolic part. And then you switch off the hyperbolic part, and you're going to see that you have more trouble with stability due to the diffusive part. And particularly because of this, I'll write soon what is the condition for the heat equation to be stable. Okay? So the heat part will make the time stepping more stringent than the transport part. Okay? And then you say, okay, blah, blah, fine. I mean, some problems, that's what you have to do also. You don't want to, whatever. But then there's a next step for making this problem a little more sophisticated. And let's see if any of you knows what's the name or the keyword for the heat part. I'm always happy when I don't get an answer, which means more information to share with you. Have you heard of Crank-Nicholson? Right? Good. So Crank-Nicholson is a method which is, and that's why I teach the numerical ODs before, which is the trapezoidal rule version for PDEs, which is this guy here, because this guy gives me a headache in terms of delta t, making delta t very small, smaller because of stability. Then this part, I make it implicit, like the trapezoidal rule. Look that this is the second derivative at time n. So I can make an average, a half of this plus a half of this guy at time n plus 1. That's like the trapezoidal rule. But it's called Crank-Nicholson for PDEs. And it has much better stability properties, very good accuracy, the same accuracy, and that's usually the method you should use. And for this case, just dealing with the matrix, then you have to maybe invert a system, blah, blah, blah. There's ways of doing it. We'll talk about this later. But you see, then similar things from OD coming into play here. Okay? So because also we have a class just after this one, I have to erase the board. So I'll finish here, which is a good point, because then next class I'll come back to this equation. I'll give you the stability restriction due to this part. You can see the notes. It's more stringent than this part, right? So if you make a delta t to satisfy this guy, you are satisfying this guy also. But then you can make things better by doing the trapezoidal rule for this guy, which is the Crank-Nicholson. And blah, blah, and then we'll talk about this next class. Okay? So I think this is a good point. Yeah, 5 minutes.